Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Fauzan ZAKWAN bin Muhammad Faudzee. I am from group LO2P2. So today I would like to talk about on the Gibbs phase rule using phase diagram of water. So without further ado, let's start with the introduction on the Gibbs phase rule. Initially, the Gibbs phase rule is founded by Josiah Willard Gibbs in 1875, an American scientist who made significant theoretical contribution to physics, chemistry, and also mathematics. This rule actually served as purpose to determine the relation of changes in phases of a substance, normally in conjunction to the temperature and pressure. So this is stated in his thermodynamic study on the equilibrium of heterogeneous substance. It also helps on characterizing the chemical state of a geologic system. Alright, so basically, Gibbs phase rule is the number of intensive variables that must be defined to determine the state of a system. What does it mean is variables comes in two variables, which is extensive or intensive variables. So variables is basically a property of a system. So let's say I have a glass of water, so from there I can know the volume, the mass, and the number of moles of the water. This is the extensive variables. They depend on the quantity of that system. Another one is intensive variables, where it does not depend on the quantity of that system, such as temperature, pressure, and also density. Hence, the Gibbs phase rule is only work on intensive variables. Next, what does state that we are looking at? So basically, it is all the knowing variables of the system, which is the phase, the number of phases, and all the things that I've mentioned before, such as temperature, volume, mass, pressure. Those are the states. Okay, so the Gibbs phase rule could actually be expressed as follows. F equals to C minus P plus 2, where F is the number of intensive variables that we would like to determine before we can find the state of a system, such as temperature and pressure. C is a number of components or a substance. So let's say if I have a water in a jar, that would be one component. If I have water and oil, that will be two components. And if I have water, oil, and salt, that will be three components. As for P is the number of phase. So in this case, if I have just ice, there will be one phase. If I have ice, water, and steam, there will be three phases. As for value of number of 2 is only a constant value, which represent the variable of pressure and also temperature. So right now, I'll be explaining further on the Gibbs phase rule using phase diagram. In this video, I'll be using phase diagram of water instead of carbon dioxide. So let's take a look on the phase diagram if you have water in a solid state of ice. By using the formula F equals to C minus P plus 2, we can calculate that for C we are using water, so 1. Then for P we only have one phase, which is solid of ice, so 1 plus 2. The answer will be 2. Hence, we will have two intensive variables. This means by looking at the diagram, it can be said that the temperature could be in any reading below 0, such as negative 10 degrees Celsius, negative 8 degrees Celsius, or negative 5 degrees Celsius, but it will not depending on any pressure. Let's say if the temperature of the ice is now at negative 10 degrees Celsius, the pressure could be vary. It could be 1 atm, lower than 1 atm, or higher than 1 atm, as long as the solid state of water does not change, which means in the ice state, proving that during this state the temperature and the pressure does not depend on each other. Okay, next, let's see what happened when the ice started to reach at the melting point. Using the same formula, the number of components is still the same, 1, because we're only using the same substance of water. This time, the number of phases is 2, as we are having liquid and solid at the same time. Hence, the F is equal to 1. So based on the diagram, we can know that the temperature now is depending on the pressure, as at 1 atm, it touches the line between the water and the ice region. So at the line where it intersects, the temperature could be determined, which normally occur at 0 degrees Celsius. The same goes if we do not know the pressure. By using the temperature, we could determine the pressure once it touches and intersects at the line between water and ice region. Alright. Now, as the phases of water changes to liquid state, by using the formula again, where number of components remains the same, but the phase is back to 1 as we only have liquid state, the answer will be 2, the same as solid state. the temperature could be varied at 10 degrees Celsius, 50 degrees Celsius or 80 degrees Celsius. The pressure again will not depend on the temperature, where it could be more or less than 1 atm at the same temperature as long as the phase does not change and the temperature is still in its limits and range. Now, in the evaporating point, it also follows the same situation during the melting point. The difference is that the number of phases is now contributed by the liquid and gas state. Hence, only one intensive variable that is need to be determined. So based on the diagram, we can know that the temperature is now depending on the pressure, as at 1 atm it touches the line between the water and steam region. So at the line where it intersects, the temperature could be determined, which normally occur at 100 degrees Celsius. The same if you do not know the pressure. By using the temperature, let's say at 150 degrees Celsius, we could again determine the pressure once it touches and intersects a line between water and the steam region. Lastly, during the steam phase of gas state, the same thing applies much like the liquid and the solid state. Since now it has two intensive variables that needs to be determined, the pressure and the temperature is not depending on each other, as again the temperature can be at 120 degrees Celsius but have very invalid pressure, where we could have pressure at 1 atm or 0.5 atm as long as it is within the steam region and vice versa. Alright, now there is one more condition where solid, liquid and gas existing at the same time, where in the diagram it can be seen at the triple point where all the condition meets. So basically, using the same formula with the same number of component, which is 1, because we are using the same substance of H2O, but this time the number of phases is 3. Like I mentioned before, resulting the answer is 0, which means 0 independent variables that needs to be defined. So by looking at the diagram, it makes sense that there is only one pressure and only one temperature that this condition can occur, and there is no other value of reading that can meet this condition. So it is normally occur at 0.06 atm of pressure and 0.01 degrees Celsius of temperature. Therefore, F is equal to 0. Meanwhile, for the supercritical phase is where the water in solid state sublimates straight away to gas at when the critical point is met at 218 atm of pressure and 374 degrees Celsius of temperature without undergo normal phase changes like from solid to liquid and gas. Okay, that is all more or less about Gibbs phase rule and how it works by using phase diagram of water. So in conclusion, until today the rule has helped the industry on determining the phase of a substance, and also the rule has proved that the changes in phases are depending on variables such as pressure and also temperature. And lastly, predicting changes in phase helps to prevent dangerous occurrence by using suitable container to hold the chemical. That is all from me. Thank you so much. Assalamualaikum.